Welcome back. In this one, we'll cover how to extract OCP data from a database called LiionDB, and then also look at how the extracted OCP can be imported within pybamm, and we'll eventually compare the results from an existing database option within pybamm. So let's begin. This first piece of code is something we've already discussed in the previous videos, so I'll directly jump to the execution. So we'll start with importing pybamm. Then we'll set the DFN model. So pybamm.lithium-ion.dfn and assign it to DFN variable. Then we've defined the pybamm experiment here, which is pybamm.Experiment discharge at 1C until 2.5 volts. Set it as exp. Then imported pybamm.ParameterValues from Prada 2013 database and assigned it to param. Then called pybamm.Simulation, passed on DFN, experiment, and parameter values. Then we do sim.solve, and since we already have the experiment defined, so we don't need time definition explicitly. And finally, solve.plot. So with this, we are now discharging at 1C up until 2.5 volts, and it's a LFP chemistry. So you can see how the voltage curve corresponds to our LFP chemistry cell. Now, let's look at this database. LionDB is an open source database for DFN model parameters, which is extracted from various literature available online. And what is it's very easy to use. So for example, we can go to parameter dashboard, then select the type of material we are looking for. So it's in this case we are looking to capture the OCP curve of LFP. So we can go to directly the positive electrode, then select half cell OCV. There are various other options like diffusion coefficient, particle radius, maximum concentration, and many more, which you can explore. So this video will stick to OCV. Then you can select LFP here. And once you select this filtering options, then it basically lists down a filtered set of data from its database in the background. And you see a table which shows the material, the paper from which it was derived, some notes about the same. So, for example, the second entry is derived for charge and the third one is derived for discharge. So this way you can get easy access to all these material OCPs from the respective relevant papers. In this example, let's go ahead with the second one, 325. So we'll just go down and select 325 from the list. Although we are doing discharge, so let's check which one corresponds to discharge. So this is the third one. So let's go back to the third one instead. In a future video, we'll also look at hysteresis. So there we'll also take charge and then compare both of them together. But for the time being, let's stick to discharge. And then at the bottom, you see the function as a plot. You can also do plot log scale or see the function. So in this case, we're interested in extracting the function. So we can just go here, see function, and simply copy this out. So once you copy this, again, there are some references which you can look at if you want to further review how the data was extracted from experiments. You can also go into the paper URL here. Now coming back to our notebook, so this is where we were, and next step is to now plot instead of using the default plotting library, now we want to plot and compare. So let's remove this and assign t1 and v1 to variables. So we'll call t1 equals to solve time. Need to be careful in the syntax. And it's very simple to also understand how this strings, which strings to be used. I've covered that in the previous video. You can go back and check it out. But we don't have to like remember all these. There's a simpler way of extracting it from the right set of commands. So assign voltage here dot entries, and next step, we will import the function that we extracted. So we can just paste it out here and run it, so that this function is present in the notebook now and can be called anytime. And this function is basically a set of empirical relation with coefficients which are defined here, and this is basically the curve fitted equation based on the raw data from experiments. So next step is to now perform a parameter update. So we have param.update, and we would like to update the positive electrode OCP. Now, the way to extract the exact string is fairly simple. We just need to go to the param value and then look at what's inside it. You can just type in param here, and then we are good to see what's inside it. So if you scroll down, what we're interested in is to update the positive electrode OCP. So OCP is this is where it's defined. So we just need to update this particular key in this dictionary. We can copy this name and then go down and put this string here. So we would like to update this with a value of function, and the function is basically defined here. So we just need to assign this function here, and we are good to go. Next, we'll again need to run the simulation, so we can also copy it from here. So sim equals to this pybamm.Simulation param, and then sol equals to sim.solve. Now instead of overriding t1 and v1, will update it to be assigned to a different variable t2 and v2, and then run it. And finally, we would like to plot these two together, so we can do import matplotlib.pyplot as plt, then plt.plot. The first plot we want is t1 comma v1, and let's give it a label Prada 2013. Then we have plt.plot, or we can basically also copy this out here and update it to LiionDB. Then can do plt.legend and plt.show. We also need to Okay. Yeah, probably this one messed up with our function definition. Let's try again. Oh, okay. So I forgot to update it to T2 and V2 here. And now we see the difference. So we can clearly see Prada and LiionDB have different OCP in the background. And that's true because we used a different set of data set. So even LFPs can have different variants. And if you want to recreate Prada 2013, we can then also go back here and select one of these two. So this is how we can define OCPs, and also we need to be careful that OCPs are different for charge and discharge due to hysteresis in case of LFP and some other chemistries too. And what we see in pybamm by default is kind of an averaged value of OCP between charge and discharge, which might lead to differences. So in one of the next videos, we'll look at how to add separate OCPs for charge and discharge and capture hysteresis. So thanks for watching. Hope this was useful.